Today is September 23rd, 2011, and this is AP Statistics at Berkeley High School, and this is the finishing up of the 2-2 lecture. We started this lecture by talking about data sets that are distributed normally, this very, very special bell-shaped, single-peaked distribution that shows up naturally in so many places that it's the distribution equivalent to pi or e. We've been given some new tools in the form of the normal distribution table, and we are putting that table to work. So let's take a look at some more problems having to do with the normal distribution table, and let's summarize the kind of work that we've already done. If we're doing work with normal distributions, it's easiest to solve these problems first by looking at the variable x. Now, what do I mean by x? I mean, x is in a real data item. We might express the question, how many young American females are shorter than 6 feet tall? But we should express that problem in terms of x. I'll write it up here. What proportion of American females are shorter than 6 feet tall? Problem stated in terms of x, the real variable that we're looking for. All right? Our second step is going to be to draw a picture of what we're looking at so that we have a feeling on the intuitive side what the answer might be. So I might draw a picture, make a beautifully drawn normal distribution. Let's remember that the mean height of young American females is 65.5 inches. That the standard deviation is about 2.5 inches. And to get up to 72, we're about probably around 3 standard deviations above the mean. Now let's be more exact. This would be 68. This would be 70.5, and this would be 73. Oh, so to be 72 inches or shorter is essentially going to be about here or below. That's a lot of people in our distribution. So we're going to expect an answer that's going to be some value that's probably pretty close to 1 or pretty close to 100%. Right. Now we're going to perform some calculations. Well, one of the things I'm going to calculate is, instead of stating the problem in terms of x, I want to state the problem in terms of z. A female who is 72 inches is how many standard deviations above the mean? Well, by our rough estimate, it's somewhere between 2 and 3 standard deviations above the mean. Can we do that calculation a little bit more precisely? The z-score for a female 72 inches tall is going to be what? This is where I really need your help, Abby. For those listening to this broadcast, I only have one student in the classroom right now. Seniors are at their senior breakfast getting their pictures taken. 2.6. So a z-score of 2.6 represents someone who is a young American female who is 72 inches tall. Right? So I'm going to restate this problem in terms of z-score. What is the probability that a z-score is lower than 2.6? And that is when we return to our normal distribution table. Our normal distribution table is written so that if we look up a z-score, we find the proportion that is at or below that value. Abby's got hers out, and I'm going to bring out my really big distribution table. I'm going to look down the first column for a z-score that's positive 2.6. It's going to take some scrolling down to get there. There it is. There's the row that's got 2.6, and if I want 2.60, I'll be in the first column, 2.61, I'll be in the second column, but I am essentially going to be in that row and that column at that intersection. And that proportion matches our intuition based on our drawing. So we believe that the proportion of the population that has a z-value less than 2.6, which matches up to the proportion of the population of young females that are shorter than 6 feet tall, is 0.9953. And we can put that in there. 0.9953. Okay? How did we do those calculations? We standardized the x value. We changed it from an x value to a z value and restated the problem in terms of that z value. That's the part that we did in red. Then we used table A, sometimes also known as the Z table, also sometimes known as the table of normal probabilities, to find the area under the normal curve that matches up with our statement. Right? So this is our 4-step process. We stated the problem, we planned our solution to the problem, we performed the calculations. That last step, I believe, is conclusion. So what is our conclusion? What's the conclusion at the end of our problem? The probability that a young American female is less than 7 feet tall, 6 feet tall, is about 99.53%. We write our conclusion in the context of the problem that we just solved. Right? All right. Should we try this again with a different problem?
Sure.
Sure. Okay? When Tiger Woods hits his driver, the distance the ball traveled can be described as a normal distribution with a mean of 304 yards and a standard deviation of 8 yards. What percent of all of Tiger's drives fall between 305 yards and 325 yards? So, plan.
Would you express it in terms of the value x?
We're going to express this problem in terms of x. What proportion of Tiger Woods' drives fall between 305 and 325? All right? Second step?
That was state, Mr. Fedor. That wasn't planned.
Oh, okay. So this is actually step 2?
Yeah.
So there's our step 2.
No, state is to express it in terms of x. Then we have to plan is to draw the distribution, shade the area of interest.
Okay, so this is step 1. Whoops. Oops, if I put the eraser. So let's go ahead and step 2, let's go ahead and draw that picture. Another beautifully drawn normal curve. Yours is very nice too. Okay, center of this normal distribution is
304.
304. Standard deviation is
8.
8 there. So this is going to be 312. 320. And then going down, we're going to go to 296. If we go down another 8, we're going to be at 288, something like that.
Yeah.
Okay, and what portion of the curve are we looking for?
Between 305 and 325.
Okay, I'm going to say 305 is about there, and then 325 is about there. So there's the portion of the curve I'm looking for. Can you give me a rough guesstimate of what you think that probability is going to be? What proportion, what percentage?
It's going to be a little less than 50, or a lot, I guess, some less than 50.
Something less than 50%.
Yeah.
Okay. And we want to do that because when we get the answer, we want to say, does that answer make sense? Okay. All right. So, step 3, perform the calculations. Well, we're going to say the probability of being between 305 and 325 is going to be the same as the probability of being between a couple different z values. And we got to figure out what those z values are. The first z value is going to be 305 minus 304 divided by 8, which is going to be 1/8, which, if I remember correctly, is 0.125. The second z value is going to be 325 minus 304 divided by 8, which is 21 divided by 8, which is going to be 2.625?
Yep.
2.625. Okay?
I'm not
Why don't you get your picture?
It's done.
Oh, why don't you have breakfast?
I don't want to go.
You didn't want to go? Because Emma wanted to be near us.
Emily, sorry. Emily.
Did you finish your test?
No.
You haven't taken your test.
I'm taking this.
You got to take your test.
Exactly.
So
How long
that's,
is this hour though?
it's shortened. It's 50 minutes.
Yeah, like
What do you
this could get any shorter. They had to make it 50 minutes.
Well, I mean, but you got to get the assembly in, and you've got a lot of
Should be
things.
after school. It shouldn't be. Just saying.
You got to add some more to your sign.
No, because if I start protesting the pep rally, I'm gonna get in serious trouble.
Well,
When's the hour actually over though?
Some senior.
I don't know. Well, take our normal start time and add 51. So that would take us to 7:31, I think.
Yeah. Okay.
All right. All right. We're in the middle of recording the lecture.
All right.
Okay. So you're just going to sit down and participate in the lecture, and you're going to watch the beginning of it later.
I need a drink really quick.
Yeah. Go ahead.
All right.
This may make for an interesting recording. All right. All right. So we're now going to say, okay, the probability that the calculation we're going to make is going to be being between these two z values. And what we're going to do is we're going to look up those probabilities individually. We're going to subtract the larger probability from the smaller probability. Now, Abby is looking it up on the probability table. I'm going to bring it up as well. And you're also going to note that the first number that we're going to look up, the bigger the two number, 2.625, we can't go to that decimal accuracy. So we're going to round. So we're going to look up 2.63 on our table. 2.63. So we're going to be in the 2.6 row, and we're going to cross-reference it with the 0.3, the 0.3 column. Okay. Emma, why don't you sort of take yourself away from all this action?
The action?
Yeah.
Okay.
All right. So 0.9957 is our first number.
Far enough?
Yep, that's great.
With that corner by yourself.
Okay, 9957 is our first number. And now we have to do the same thing. And we need to look up, if we could, 1.25. But instead, we're going to look up 0.13. Hi, Paul.
Sorry, I'm interrupting the lecture.
No, sit down. Join the fun.
Thank you.
Okay, so here's my 0.1 row, and here's the 0.3. So our cross-reference number there ends up being 0.5517. So let's carry that number forward. 0.5517. Hi.
Sue, hi. Hi,
I'm sorry?
Sue.
Hi, Sue.
How are
Okay,
you?
fine.
I just gave
Oh.
you past it.
Very good.
All right.
That should be interesting. Here's the issue. It says West Gym because she's probably at the senior breakfast.
Okay, they just gave them to me. Same thing with you, both?
Yeah.
Okay, great.
So what I'm going to do,
Thank
if she
you.
does show up here, I'm going to send her to the student center.
Okay,
All right,
thanks.
but she's probably the West Gym.
Okay.
It showed
Okay.
me back till 9:15.
All right. So let's finish off this calculation. And I'll need some help here. What do you got, Abby?
0.444,
Point
3/4.
444, and I'll put the 0 on the end.
All right.
All right? And as per our earlier conversation, look at the area that is shaded. You said it's going to be less than 50%. That number is near but less than 50%. I would say that we're got an answer that's approximately correct.
That's how you do that? Because I was doing the homework, like
Upper minus lower.
upper minus lower, and then find the z-score, and then subtract those z numbers to get percent.
Right.
Correct.
Okay.
What was
Or
that?
if you want it more visually, here's me, and here's the distribution, and here I am at a z value of 2.625, and there's all that value there, and that's my 99.57. So this one in blue. Here's me doing the same distribution, and here I am at 0.125 z value, and there's the 5.5517. And essentially, what I'm going to do is I'm going to take the black area, and I'm going to subtract off the blue area, the part that I don't want anymore. I don't want the stuff that's less than 0.125, which is equivalent to the drives that are less than 305 yards. Okay? There's our calculations. Conclusion. What's our conclusion?
He's 44.4% of his drivers are between 305 and 325 yards.
Very well stated. Okay. Oh, I don't know if we use the word of his drivers.
No.
Of his,
I thought drives, I
of his
was-
drives. He's using the driver.
He's this way to change drivers every yard. It gets really annoying, and he's late to everything.
Actually, it's reminding me of a They Might Be Giant song called AKA Driver. You don't know who it is.
I know the band, I don't know the song.
Yeah.
Oh,
and
it's off of one of their early albums. Hey, why don't you come up and join us?
all right.
Yeah, I'm just excluded.
Or
Stay back
if
there.
you don't, well, you are excluded because you're taking a test. If you want to feel more excluded, we can put you in the hall. No? No. No.
All right, I already moved to the back corner.
Okay. You Gandalf?
Oh,
Wrote on the
you saw
tissue
that?
belt.
Done.
Wrote it.
Shall pass.
What? Does he say none shall pass or
He says
you
you
shall
shall
not
None shall pass
pass?
this class, or none shall pass the tissue ballots.
Tissue box.
Okay. Phew.
Pandora's box in there. Yeah.
That'd be none
That's a,
shall
that's a totally different
Oh.
myth.
None shall open.
I'm mixing
the
it up,
tissue
guys.
box.
I'm mixing it up.
False tissues.
What's the name of that monster that he's?
The Balrog.
That's it.
I love it.
I just started reading The Hobbit with my son.
Good.
How do you like it?
Well, I've read it several times,
That's
so.
like a dad thing. It's like required. Every dad has to read that book to their kid.
Yeah, well, we already finished all of Narnia.
Yeah.
Oh, my dad likes.
Except we didn't read the final battle.
Yeah.
I just
that
can't-
one's
I can't-
So sad.
I can't go there yet.
You can't.
He's
traumatize
I don't know if
your
he's
son.
ready. I don't know if he's ready. I'm not ready.
How old is he?
9.
Yeah, he's not ready yet.
So we did the other 6, but we
Do
did
you like
the
people dying list? I mean, I don't mean to be like a spoiler person, but
It's like book 7 of Harry Potter. It's just disappointing.
Yeah. He just finished reading the entire Harry Potter series.
At 9, go him.
Yeah. It was his crowning achievement. He was asked by his teacher, his first grade teacher, "What are you most proud of?" And he goes, "Finishing the Harry Potter series." And I said, "Yeah, that's exactly. I am very, very proud of him as well." All right. Okay, we're in the home stretch for this lecture. Ready?
Normal distribution.
Normal distribution. Well, we've been talking about normal distribution for the entire lecture. And we said, hey, when we have a normal distribution, we've got this great tool. Okay, here's me handing, it's a great tool, right? The normal distribution table. And basically we can do all sorts of really cool calculations if the distribution is normal. Problem, not all distributions are normal. So, Paul, here's me holding up an imaginary distribution. I hand it to you,
thank you.
and I say, hey, take that distribution and use the normal distribution table. Sorry, like that. And you say, but wait, Mr. Fyodor, this table is only good if this distribution that I have in my hands,
Symmetric.
not only symmetric, because you know what? Let me draw a symmetric distribution.
Single.
Hey, there's a symmetric distribution. Can you use that distribution? Can you use the normal distribution table?
Single peak.
Okay. So, single peak. Okay.
Symmetric and single peak.
There's a single peak distribution. Can you use the normal distribution for that?
No.
Dang it.
Jeez.
It takes more than just being single peaked. It takes more than just being symmetric, okay, to be a normal distribution. And we're only allowed to use the normal distribution tools if the distribution is normal. So the question is, given some distribution that you meet on the street,
Right.
how can you find out if it's normal? How can you assess its normality? Is the way that they want you to attack the problem.
Some kind of metaphor from high school.
Well, it is always fun when math words have multiple meanings. Yeah.
It's a real.
Like, I mean, my son is studying regular polygons in 4th grade. I'm like, regular polygons, great. They have bowel movements every day? Is that what it means to be regular? So anyway, we need a strategy for assessing the normality of a data set to find out whether it's appropriate to use these tools on them. And here we go. Here's how we're going to do that. To assess normality, we're going to plot the data. What do we mean plot the data? Well, with quantitative variables, we can do a box plot. We could do a 7-leaf plot. We can do a histogram. We have those 3 plots that are sort of at our disposal here. Okay, when we plot the data, we're looking for symmetry and we're looking for bell shape. Now here's the trick. Looking and finding the symmetry is insufficient to say that it's normal. But if we have evidence of a non-symmetry, sorry, that's wrong. If we have evidence of it being asymmetric, that's enough to say it can't be normal. Evidence of skewness or asymmetry is enough to say whatever we have, it's not normal. Evidence of symmetry is insufficient, though, to say that it is normal. Well, I mean, it's the words here are awkward, but you know, you look at me. I make a statement. I'm an NBA All-Star. You just have to produce one piece of evidence that contradicts that, and that's enough to say, oh, you are not an NBA All-Star.
I can't think of anything that would say you're not an NBA All-Star.
Well, that I drive a 10-year-old car with
Is working
100,000
at a high
miles,
school.
that I'm working at Berkeley High School, that I'm 5'7" on a good
You're
day.
under the radar. You can be like Allen Iverson.
I lack felony convictions. No, Iverson never got convicted. He was only charged.
Of what was he
I
trying
think he was charged with rape.
Yikes.
Go basketball players. That's a trend amongst them.
And they
Yeah.
moved too. It was
Oh, maybe I'm confusing him with Kobe Bryant.
Yeah, you may be.
Okay. All right. So anyway, so if we see evidence of asymmetry or skewness, that's enough to say not normal. All right. We could check to see whether the data actually follows the 68, 95, 99, 7 rule. Now, as we saw in yesterday's demonstration, we were around. You know, we were 50% instead of 68. We were at 88% instead of 95%. We were at 100% instead of 99.7. Okay, so there's a little bit of wiggle room here, but we can see, does it roughly follow that pattern? All right. For example, I gave you the thing, here's a symmetric distribution. Would it follow the 68, 99, 90, 99.7 rule? No, 100% was within 1 standard deviation as compared to 68. I mean, that's really far. That's a judgment call. Ah, but maybe we have one tool to rule them all.
And there was the Lord of the Rings connection.
Yes.
bring me my long sword.
Okay. Glamdrill. Is that right? Is that the right one of the swords?
What's the one that Aragorn uses when That's
Aragon?
because- wait, what? I was saying-
Okay, that's it. I'm leaving. Bye.
I have a hard time pronouncing it as well.
What is it?
Because you gotta,
Aragon is the dragon by the 16-year-old guy. Aragorn is the
Aragorn,
right.
not to be confused with Aragog, who is the
Who's
large spider
in Harry Potter.
in Harry Potter.
Because everybody's ripped off Tolkien for
Well, I
a
mean,
decade, 2 decades, 3 decades.
like Tolkien invented dragons, like
No,
Tolkien
no,
invented
no, but
giants,
the
or
name
trolls
thing.
or goblins.
The name thing. I mean,
Yeah, well,
I can pass Legolas.
Lego
Dude,
Lost?
here's
Did you
guns.
say Lego Lost?
Lost.
that's what we found
Lego
in the
Lost.
closet when we cleaned it out. Oh, here's the Lego Lost.
You're such. You guys, give me
All right.
some slack, please.
Okay,
Try
so
here.
the one tool that we really can, is the go-to tool for assessing normality, though, is called the normal probability plot.
Normal probability.
The normal probability plot. Now, luckily for you, the normal probability plot is actually built into your calculator. You have 6 different things that your calculator does. One of them is called the normal probability plot. It's the one you didn't know what it did. It's the sixth one. I'll show you, I'll demonstrate in a second. All right? So the normal probability plot produces, given a list of numbers, it produces a graph. Okay? If those points on the graph are close to being a straight line, close to being linear, our conclusion is that the data is normally distributed. All right? If the normal probability plot is not linear, our conclusion is that the data is not normally distributed. All right? Outliers appear to be points that are far away from the overall pattern of the data. Swerves in the data, in the normal probability plot, are representative of skewness. All right? So I've got to do 2 more things with you on this lecture. One, we have to look at various probability plots and be able to say normal, not normal. And 2, I have to give you the demonstration of how to create those plots ourselves. All right? So here is a data plot in histogram form of survival time in days. All right? And looking here, you would describe this data as being
Right, Steve.
skew right. Yes, right skew. All right? If I take that same data and throw it into a normal probability plot graph, what I get is data which is not linear. Not only not linear, but when I sort of connect the beginning and ends of the data, it goes above that line. So we can actually look at this plot and we say, oh, the line's going above. That data is not only not normal, but it is right skew. All right? Okay. It goes to the summary. We have to do some more work right now. All right? So let's add a blank slide. Okay? What if the data is left skew? So if we have a histogram, which is left skew, we're going to get a normal probability plot in which the data is going to swoop like this. Okay? And our line that we think would work and this normal probability plot falls underneath it. All right? How about we actually create a normal probability plot? Are you ready?
Yeah.
I'm going to switch over to my calculator. I'll do it this way because it's so cool. All right, so here's my calculator. Let's fill up a list with data that is normal. All right? You don't know how to do this yet, and I'm not going to explain why it works.
Okay.
All right? But you're going to type this in your calculator. Math. You get that menu. PRB. Probability. Option number 6 is rand normal. Okay? Rand normal says I want to create a bunch of random numbers, but they are going to follow a normal distribution. Right? Let's do randomly chosen females, and we're measuring their height. I say that the mean of this normal distribution is going to be 65.5. The standard deviation is going to be 2.5. And how many females do we need?
8,
No, more than that. 50.
18.
18. 50. Okay? And what do I want to do with this list of randomly chosen females? I want to store it into L1.
I know you can do that.
Yeah, stick with me,
It's
Paul.
more than just puzzle packs.
He's like, I'm all over block, dude.
I love Black Dude. I have an 84 plus. That's silver edition.
All right,
Oh man.
all right. So here's me creating all those people. Oh, there's our first female. She's 61.5 inches tall.
Okay, why does mine say 68?
Because it's random.
Oh, gotcha.
They're actually producing different random number sets.
Alright.
All right? Now, what could I do? I could plot that data. Right? I can go into plot 1, and I could say, turn the plot on, and I'll choose histogram for right now. Just so that we can see that it looks normally distributed. All right? I chose histogram, and I'm going to go, my favorite zoom, zoom 9. Oh, where's zoom 9? Somewhere in here. Probably 2 after 7. Zoom stat, which says, format my window to match the data in my plot. And when I do that, I get something that's roughly normal. The bigger my data set, the more normal it will look, by the way. Certainly doesn't look skewness. It looks like this one's just a little too tall, this one's a little too short, but
I mean,
I'm gonna call it roughly normal. Right?
mine kind of looks like
Right?
that,
Let's do the normal probability plot for this though. Are you ready? Normal probability plot will be second stat plot. Still going to use plot 1. But when I go to choose which plot I'm using, instead of histogram, instead of box and whisker plot, I'm going to that last option. That's the normal probability plot. You never knew what it was for. It's for doing what we're about to do, assessing the normality of a data set. And again, once I choose it, I'm going to do zoom 9, which will format my screen. And what do we see? We see a data set that is we see a graph that's approximately linear. Our conclusion based on that is that the data set is approximately normal. A linear plot leads to the conclusion that the data set is normal. And once we say that it's normal, hooray, now we can use the normal probability tools, the tan sheet. All right? Now your data set doesn't look all that linear. It's a little skewed. That happens. Okay. All right. And I don't know. That's about it. That's about it.
Yay.
Okay? So, in conclusion, normal distributions appear naturally. Normal distributions can all be standardized by converting all of the data into z-scores, and then every normal distribution that converted to z-scores, they all look the same. Table A gives us information about that normalized data that allows us to do calculations having to do with probability. For all normal distributions, it fits what's called the empirical rule, the 68, 95, 99, 7, that approximately 68% of the population occurs within one standard deviation of the mean. Approximately 95% of the distribution is found within 2 standard deviations of the mean, and approximately 99.7% of the population occurs within 3 standard deviations of the mean. Again, we call that the empirical rule. All right? And in the next chapter, we'll look at scatter plots and linear regression. We'll be looking at 2 quantitative variables at the same time.
Mr. Vader, what do you
Oh,
want me to do?
what's up, guys?
I got to 12.
You,
I want to